Hmm. Chapter 5 of System Design Interview. So this chapter has design consistent hashing. To achieve horizontal scaling, it is important to distribute requests and data efficiently and evenly across servers. Consistent hashing is a commonly used technique to achieve this goal. But first, let us take an in-depth look at the problem. The rehashing problem. If you have n cache servers, a common way to balance the load is to use the following hash method. Server index equals hash key modulo n, where n is the size of the server pool. Let us use an example to illustrate how it works. As shown in table 5.1, we have 4 servers and 8 string keys with their hashes. So key 0 का hash है 183.58617 and hash modulo 4 is 1. Key 1 का ये hash and hash modulo 4 is 0, and similarly we have 8 keys and 8 hash values, and then we are calculating hash modulo 4. So this is a general technique. If you have n cache servers, a common way to balance the load is to use the following hash method. Server index equals hash key modulo n. So basically, we have a hash key, and on the basis of that value, we can select which server we want to send. Fetch a server where a key is stored. We perform the following. We perform the modular operation f of key modulo 4. For instance, hash of key 0 modulo 4 equals 1 means a client must contact server 1 to fetch the cache data. Figure 5.1 shows the distribution of keys based on the table 5.1. Server index equals hash modulo 4. Server index equals 0, 1, 2, 3, and servers, and we have keys that are being mapped to the servers. So हमारे पास ये values थी, and what we are doing is we are mapping them, right? So what we are doing is like we're mapping these values. So for example, we have obviously अगर hash modulo 4 है, hash n है, hash modulo n है, so the number of servers that we'll have obviously are equals to n, और वो start होंगे 0 से लेके n minus 1 तक. So in this case we have 0, 1, 2 and 3. So these are the servers that we have. And इसके हिसाब से हम keys को segregate कर सकते हैं. So जैसे key 1 will be on the server, oh my bad, it would be 0, मतलब server का number है 0, 0, 1, 2, 3, राइट. सो यहाँ पे हमारी होगी की 1, एंड फिर हमारी की 3 भी होगी यहाँ पे, एंड दैट्स इट. और सर्वर 1 के लिए हमारे पास होगा की 0 एंड की 4, एंड सिमिलरली सर्वर 2 के लिए हमारे पास होगा की 2 एंड की 6, एंड फॉर सर्वर 3 के लिए हमारे पास होगा की 5 एंड की 7. ठीक है. So every server in this case has 2 keys, and obviously the total number of keys are 8 here. So this is how they have done this. This approach works well when the size of the server pool is fixed and the data distribution is even. However, problems arise when new servers are added or existing servers are removed. For example, if server 1 goes offline, the size of the server pool becomes 3. Using the same hash function, we get the same hash value for a key, but applying modular operation gives us different server indices because the number of servers is reduced by 1. So we'll have this. And now as we can see here, the load on the server 0 has increased by almost twice. And the load on the server 2 has decreased by 2 also. And so this is not very efficient, right? Because server 0 पे बहुत ज़्यादा लोड हो गया है, server 2 पे बहुत कम लोड हो गया है. So the load is not balanced at all here, right? As we can see here, like यहाँ पे भी बोला है इन्होंने, this approach only works well when the size of the server pool is fixed. है ना. तो अगर ये फिक्स रहेगा तो देन इज वेल एंड गुड, हमें पता है कहाँ पे कितनी रिक्वेस्ट जाएंगी एंड स्टफ. एंड द डेटा डिस्ट्रीब्यूशन इज इवन. डेटा डिस्ट्रीब्यूशन इवन होने से क्या होगा, द लोड ऑन ईच सर्वर विल बी डिस्ट्रीब्यूटेड इवनली, राइट. एंड दे हैव शोन दिस कि क्या यहाँ पे क्या हुआ, राइट. की 0, की 5, की 7, ऑल दीज कीज आर ऑन द सर्वर, लाइक उस पर पहले से की 1 थी, राइट. बट अब 3 मोर कीज आ गई हैं, एंड सर्वर 1 से सारी चली गई हैं, तो सर्वर 1 पे कोई लोड ही नहीं है. right? So as you can see 0 1 2 3, right? पहले हमारे पास 4 servers थे, so वहाँ पे load इसलिए नहीं है क्योंकि we removed it, my bad. So yeah, this is the current state, right? As shown in figure 5.2, most keys are redistributed, not just the ones originally stored in the offline server, server 1. This means that when server 1 goes offline, most cache clients will connect to the wrong servers to fetch data. Yes, this causes a storm of cache misses. Consistent hashing is an efficient technique to mitigate this problem. तो अब इसमें हुआ क्या? Since or since the key values are hashed by a different function now because the number of servers has decreased, तो अब जैसे अगर एक यूजर was going to server 2 to fetch their cache data, पर अब मॉड्यूलो 3 होने की वजह से लेट्स से उसकी वैल्यू 0 हो गई, सो ही विल गो टू सर्वर 0 एंड वहाँ पे उसका डेटा होगा ही नहीं, तो दिस विल लीड टू अ कैश मिस एंड this will cause a storm of cache misses. So to solve this problem, we use consistent hashing. So consistent hashing, as quoted from Wikipedia, is a special kind of hashing such that when a hash table is resized and consistent hashing is used, only k by n keys need to be remapped on average, where k is the number of keys and n is the number of slots. In contrast, in most traditional hash tables, a change in the number of array slot causes nearly all the keys to be remapped. Yes, consistent hashing is a special kind of hashing such that when a hash table is resized and consistent hashing is used, only k by n keys are remapped, where k is the number of keys and n is the number of slots. Okay, so consistent hashing करता क्या है? Like as we have seen, normal hashing में, normal modern hashing में, almost every single key was remapped, right? तो इन्होंने जैसे कहा है nearly all of the keys have to be remapped. So this is very slow, right? And consistent hashing is a technique in which only k by n keys have to be remapped, where k is the total number of keys and n is the total number of slots. So hash space and hashing. Now we understand the definition of consistent hashing. Let us find out how it works. Assume SHA1 is used as the function f, and the output range of hash functions is times 0 times 1 times 2 and till times n, right? In cryptography, SHA1 hash space goes from 0 to 2 to the power 160 minus 1. This means that 0x corresponds to 0 and 0n corresponds to 2 to the power 160 minus 1. And all other hash values in the middle fall between these values. By collecting both ends, we get a hash ring x0 and xn. Okay, okay, so we just connect both the ends, right? Hash servers. Using the same hash function, we map servers based on the server IP or name onto the ring. Figure 5.5 shows that 4 servers are mapped on the hash ring. So these 4 servers are mapped on the hash ring. So we have server 1, server 0, server 1, server 2 and server 3. These 4 servers are being mapped on the hash ring, and this hash ring is not just a ring, right? Here they have shown it like a normal ring, but it's not a normal ring, right? It has um, it has these slots. So this is x0, this is x1, this is x2. ऐसे करते 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 यहाँ तक आ जाएगा x2 to the power 160 minus 2 पे ऐसे, like these are like slots here, right? These are slots. So अगर हम server assign कर रहे हैं तो we are assigning to a slot, है ना? This is not just like normal ऐसे ही randomly assign कर दिया. We have assigned them to a slot. Hash keys. One thing worth mentioning is that hash function used here is different from the one in the rehashing problem, right? There is no modular operation. As shown in figure, 4 cache keys, key 1, 0 are hashed onto the ring. Here you can see key 0, key 1, key 2 and key 3, right? So these are the servers, you know, and these are the keys that are mapped here. Server lookup. To determine which key is stored on, we go clockwise from the key position on the ring until a server is found. Figure 5.7 explains this process. Going clockwise, key 0 is stored on server 0 and key 1 is stored on server 1, key 2 is stored on server 2 and similarly key 3 is stored on server 3. Add a server. Using the logic described above, adding a new server will only require distribution of fraction of keys, right? In figure 4.8, a fourth server is added. So इसमें redistribution किसका हुआ? खाली k0 का हुआ because now, right? So K1 and K2, and they all of them remain the same. Let us take a close look at the logic. Before server 4 is added, key 0 was stored on the server 0. But now key 0 will be stored on server 4 because server 4 is the first server it encounters by going clockwise from key 0 position. The other keys are not redistributed based on consistent hashing problem. Remove a server. When a server is removed, only a small fraction of keys require redistribution by consistent hashing. In figure 5.9, when server 1 is removed, only key 1 will be remapped to server 2. The rest of the keys are unaffected, right? As you can see, now server 1 is removed, so we go clockwise, and server 2 is the first server we find while going clockwise from key 1. So this is mapped to server 2. So there are two issues in this basic approach. Uh, Basic steps are the consistent answer problem was इसके basic steps होते हैं map servers and keys on to the ring using a uniformly distributed hash function. So we map servers and keys on the ring using a uniformly distributed map servers and keys on the ring using a uniformly distributed hash function, right? So we are mapping all the keys and the servers on the ring using a uniformly distributed hash function. Find out which server a key is mapped to. Go clockwise from the key position until the first server is on the ring is found. Two problems are identified with this approach. First, it is impossible to keep the same size of partitions on the ring for all servers, considering a server can be added or removed. Partition is the hash space between adjacent servers. It is possible that the size of the partitions on the ring assigned to each server is very small or fairly large. If S1 is removed, S2 partition highlighted with bidirectional arrow is twice as large as S. Yes, because this is removed, right? So it's called partition. Basically, partition is the difference between two adjacent servers. So in this ring, the partition is almost similar when the server one is still there, right? We have this partition, this is the distance, this is the distance, and this is the distance. But when we remove server one, the partition between S2 and S0 is way greater than S3 and S2 and S3 and S0. Second, it is possible to have non-uniform key distribution on the ring. For instance, if servers are mapped to positions listed in yeah, yeah, as you can see, इसमें जो मैपिंग है सर्वर की दिस इज वेरी बैड बिकॉज यहाँ पे हम देखें कि वन जो है इट विल बी मैप टू सर्वर जीरो ओके एंड रेस्ट ऑल द कीज विल बी मैप टू सर्वर टू व्हाई बिकॉज वी व्हेन वी गो क्लॉकवाइज पहला सर्वर जो आएगा इनके लिए दैट विल बी सर्वर टू सो सर्वर 3 एंड सर्वर 1 आर सिटिंग completely idle इनका कुछ काम ही नहीं हो रहा एंड दैट इज अ वेस्टेज ऑफ रिसोर्सेज राइट a technique called virtual nodes or replicas is used to solve this problem. So we use a technique called virtual nodes to solve this problem. ये वाली problem जो आई कि all the server traffic and all the data मतलब एक ही server पे all the traffic and all the data एक ही server पे आ गया है and this is the problem. इसको solve करने के लिए we use virtual nodes. Virtual node refers to a real node and each server is represented by multiple virtual nodes on the ring. Yes. In figure 5.12, both server 0 and server 1 have three virtual nodes. So this is S0, 0, S0, 1 and S0, 2 and S1, 0, S1, 0. So these are the virtual nodes in here. है ना? So instead of just giving a server a single position on the ring, on the hash ring, हम क्या करते हैं हम virtual nodes बना लेते हैं एक ही server के लिए and we distribute them on various parts on the hash ring. तो अब इससे क्या होगा कि all the traffic will not just be on one server. It can be on its virtual nodes too. तो एरिया का स्कोप बढ़ जाता है. The scope that is covered by a single server is increased due to creating the virtual nodes on the hash ring, right? And these are the partitions and stuff. So to find which server a key we go clockwise, and as you can see यहाँ पे हमारा server 1 पे होगा. As the number of virtual node increases, the distribution of keys become more balanced. This is because the standard deviation gets smaller with virtual nodes, leading to balanced data distribution. Standard deviation measures how data are spread out. Yeah. The outcome of an experiment carried by an online research shows that with 1 or 200 virtual nodes, the standard deviation is between 5% and 10% of the mean. The standard deviation will be smaller when we increase the number of virtual nodes. However, the more spaces are needed to store data about virtual nodes. This is a trade-off, and we can tune the number of virtual nodes to fit our specific requirements, specific system requirements. Find affected keys. When a server is added or removed, fraction of data needs to be redistributed. How can we find the affected range to redistribute the keys? In figure 5.14, server 4 is added onto the ring. The affected range starts from S4 newly added node and moves anti-clockwise from the ring until a server S3 is found. The keys located between S3 and S4 need to be redistributed to server 4, right? So for example, let's just इन्होंने कहा है कि server 4 हमारा new server है जो add हो गया है, and that server is between server 3 and server 0. So पहले key 0 was pointing to server 0, but now since server 4 is closer to it, when we go clockwise, so वो server 4 पे map हो जाएगा. Yeah. So all the keys that are between server 3 and server 4 need to be redistributed to server 4. When a server S1 is removed, right, the affected ranges from S1 to S2, right? Wait a minute, what? Oh, yes. When server 1 is removed, right? Server 1 है, वो remove हो गया है. Yeah, so affected range होगी ये पूरी range S0 से लेके S1 तक, because all the nodes in between this range will are pointing to server 1, right? So this range will be the affected range, and जो इसके बाद वाली होंगी वो तो पहले ही server 2 पे point कर रही होंगी, like T2 is already pointing, तो ये affect नहीं हुई, ये वाली range affect हुई है, and all the keys here will be mapped to server 2. Yes, ऐसा होगा. Wrap up. In this chapter, we had an in-depth discussion about consistent hashing, including why it is needed and how it works. The benefits of consistent hashing include minimized keys are redistributive when servers are added or removed. It is easy to scale horizontally because data are more evenly distributed. Mitigate hotspot key problem. Excessive access to a specific shard could cause server overload. Imagine data for all these singles will end up on the same shard. Consistent hashing helps to mitigate the problem by distributing the data more evenly. Consistent hashing is widely used in real-world systems, including some notable ones. Partitioning, partitioning component of Amazon's Dynamo database, data partitioning across the cluster in Apache Cassandra, Discord chat application, Akamai content delivery network, Maglev network load balancer. And that's it for chapter 5. This is all the material. And yeah, आज इतना ही. Yes, I'll continue chapter 6 tomorrow. Design a key value store. This is very interesting. Hmm. Key value database को कैसे डिजाइन करें? Okay. This is actually a lot of content. So I'll do this tomorrow. Anyway, that's it for today.